This is a flash lecture on UV VIS spectroscopy. Let me tell you a little bit about the principle of the UV VIS spectroscopy, in this case, time-dependent measurements. So let's say in the spectrometer, the UV VIS spectrometer, you have two cell holders. One closer to you is your sample holder. The other side, the further out away from you, is the reference. So now, all the instrument is doing is just to it's comparing between those two cells. So you have a detector. You have a detector at each end of the light path. So the light is shining through the two cuvettes. Light comes out, and detector measures it. So in principle, absorbance in the time measurement, you have time versus absorbance. And in principle, when you hit auto zero, this minor difference in absorbance between the reference side and the sample side will be adjusted so that your absorbance appears as zero. That's what auto zero does. Now, your case, you have a Papain in your sample and reference side. But this is a Papain in buffer, so keep that in mind. Now, both of these are enzyme. Again, if you take the measurement right now, all the detector is doing comparing between these two lights. So again, it's showing as zero. Now imagine that you're actually adding a BAPNA in this solution. So now on the sample side, you are adding BAPNA in DMSO. DMSO is just a solvent. So you're adding BAPNA. BAPNA itself has a pretty intense yellow color. So you're adding more yellow into this. So absorbance will go up. So immediately upon the addition of your BAPNA, absorbance will go up to somewhere a little bit higher because of the presence of BAPNA. And then reaction starts taking place. So now reaction starts taking place, and then the absorbance starts going up. So you are looking at the rate of reaction. So the slope here is what you really want. Keep that in mind that when you have Papain in buffer, it doesn't really have to be Papain. So your instruction originally calls it for use buffer. And then, so just because of the instrument, the Parkin-Elmer calls for a auto zero, which adjusts the detector input to realign so that these two light paths would show up as zero absorbance, and then it's going to call for another blank, and that's why the buffer was called for. But as long as you know what you're doing, you don't really need to use buffer. You can go ahead and use Papain on both sides, and then just use auto zero anyways. Because again, all the instrument is doing is just to looking at two detector input anyways. Now, there is another way to do this experiment. If the absorbance is too high, then technically speaking, you could use buffer. So let's say you have a buffer here. And then you want to add BAPNA. But this time, let's say add BAPNA on both sides together. Now, in this case, BAPNA is added simultaneously into two cuvettes. So the detector is detecting BAPNA having a color, but added in the both cuvettes. So absorbance really wouldn't change. So it's going to be probably around 0 anyways. From here, the reaction takes place because of the presence of papain. So because of the presence of papain, so this side, the buffer side, even if you add BAPNA, reaction will not take place because you wouldn't have p-nitroaniline. But papain side, on the other hand, you would have the reaction. So reaction takes place at the same velocity as you had before. So now the alternative reaction line would be this. So keep that in mind. So this is what the alternative protocol is described at the end of the handout. So if the absorbance is too high, because if it's greater than 1.5, then you don't have enough percent transmittance for the light. So which means your data may not be good, or it may be already beyond the instrument capability to detect light. So in that case, you have to use or you don't have to do anything for your life, but this is one of the ways to do it, is to use BAPNA on both sides, but change the solvent into buffer so that the reaction wouldn't take place. So keep that in mind. All right, thank you for watching, and if you have questions, let me know.